Ooh, section 5, friends. Let's go nuclear here a little bit, huh? Learn about nuclear power. So nuclear fission is the main type of power source that we talk about, because nuclear fusion is not something that's applicable in our world yet. We haven't found a way to harness that so well. So fission is when we split things in half, the big atoms down. And so first atomic bombs we made were nuclear fission, and power plants are nuclear fission. Here's actually a fuel capsule, a fuel rod component, and this is actually a nuclear reactor core with the liquid in it, the insulator, the water present. So all of this involves nuclear fission. So what is nuclear fission? This is the splitting apart of atoms that release energy. And so that old E equals mc squared by our friend Mr. Albert Einstein comes into play here. E is energy and mass, and c is the speed of light squared. So what happens is, this is a piece of uranium-235, which we use often in nuclear reactions. We take a little neutron and we chuck it at it. And when we chuck it at it, we hit it and we break it into two pieces. So the two pieces we break it into are both radioactive, of course. But an important component when we break these two things in half is it releases 3 more free neutrons. These 3 free neutrons then go out and hit 3 more nuclei, breaking them in half, and you see how 3 quickly grows into 9. And this cascading effect, exponential growth factor, is called a chain reaction. And so this is how a typical nuclear reaction occurs. And so you can see how it goes to the boom boom level really quickly. And so scientists use basically 2 types of nuclear fuel: isotopes of uranium and plutonium, which are 2 very large molecules that are unstable. And what they do is they take and undergo that nuclear fission reaction, this chain reaction effect, by controlling that reaction and slowing it down. When they slow it down, it still produces heat and releases energy, but it does it at a rate that we can manage it. And so the way we do that is we use uranium oxide, which is 97% just regular uranium-238, which is not radioactive, or is not capable of nuclear fission. And then just 3%, a very small quantity of 235, which is radioactive. And so this is the basic setup of a fuel rod. Now, fuel rods can undergo concentration, or what we call an enriching process, which means we can add another 0.7% onto this 3, and make it almost 4%. But a very low quantity of the actual material is actually doing fission in nuclear fuel. And so if we control that reaction and we create nuclear power plants. Uncontrolled, create atomic weapons. And so nuclear fission reactions, we do them in a reactor, of course. Inside that reactor we have these long chambered fuel rods. The fuel rods fit together in these big huge clusters of fuel rods called fuel assemblies. And then those get put down, and so you can see a big fuel assembly down inside this reactor core right here. Inside each rod are these little teeny tiny pellets, which are fuel pellets, which are the 4% to 3.7% at most uranium-235 pellets, or uranium oxide. In between those, we place control rods. And these control rods absorb those extra neutrons that were flying out. Remember the ones that are creating this cascading exponential reaction? And we absorb those extra neutrons, and by doing that, we can control the rate of the reaction. We simply pull up and down on those control rods, moving them in and out of the way, and getting the reaction to happen at the rate we want. We do this in the presence of water, because water allows it to not melt down, but it is a cooling agent that helps the reactor stay stable. And then, of course, over top of the whole system, we have a containment shield to protect it from any kind of major issues. And so this is the main components of a nuclear reactor. And here's a picture of that exact process kind of laid out. Here's the general look of it. This is the containment system with the fuel rods and control rods present over here. This is a picture or breakdown of the same thing. So this concrete shielding is the containment unit. You see the reactor core has a fluid in it, and then it has the fuel rods, which are in red here, and the green rods are the control rods, which we move in and out to make the reaction happen. That water then heats up, and we push it through a system where there's a turbine where it creates electricity. Then we take and cool down that water and put it back into the system. And so it's the same cycle as the coal. It's the same cycle as the natural gas. And then we cool that down with outside things like cooling towers or water systems that enable it to work properly. So it's the exact same dynamic that we use in the other systems. Nuclear power plants are also not very efficient. 83% of the energy that's being produced in that nuclear reaction is wasted as heat. Very little, only 17% actually goes into producing electricity. So, how does it work? Well, I just explained it to you in a nutshell. And then after it's happened, we can, and so this reactor will run on these fuel cells for about 3 to 4 years. And then afterwards, those fuel rods are what we call spent. They've been used up. And they actually can have one or two things happen. They can actually take them apart. Now they're radioactive and in pretty nasty shape. They can take them and just put them into long-term storage. And they can be stored in pools of water until they cool down. That's what they're doing in this particular thing. They're taking the rods and placing them in there until they cool over time. And then they can be put in sealed concrete containers after that, and that can be above or below ground. These are spent fuel rods sitting in containment units. Most of them are stored on the site. They're typically stored on site at wherever the power plant is that they're being worked in. In some cases, after they cool down, they don't store them this way. They actually pull them out, and they process the used uranium from the other, and then they recycle it and make more pellets out of it. That happens on occasion too, but it's pretty expensive, dangerous work. So how does the system work from start to finish? You start by mining uranium. And so uranium's all over the place. This map down here shows you where the uranium concentrations are at. Of course, you see we're in Wyoming right here. So all those red patches in Wyoming are where uranium is found, and we have uranium mines in Wyoming as a result. Right? Just went down by Tisdale Mountain. Once the uranium's pulled out, it's processed and basically removed from all the gangue, the spoilings, all that kind of stuff, and it's concentrated. Once it's concentrated into uranium oxide, focusing on the 235, it's then used inside the reactor. And then after that, they need to find safe places to store all that radioactive waste that's being made. And then typical life of a nuclear power plant varies, but oftentimes they last to about 40 years. At that point in time, they can be decommissioned and shut down and sealed up and left alone. So, after more than 50 years of development and enormous government subsidies, which we've spent lots of money on, nuclear power plants just haven't kind of taken over. They were once believed to be. The promise was that we'd have limitless energy at very low cost. But in reality, that hasn't happened. So we've had multiple billions of dollars spent in construction costs, which are prohibitive to nuclear power. The operating costs and malfunction issues create higher costs. Poor management has been a factor. Public is not a fan of hearing about it and being involved with it. And because there's so much wasted energy in the system, you don't get the energy yield you want out of the system. And so as a result, here in the United States, only about 8% of our energy comes from nuclear. And so as a result, there's a lot of negativities to it. In 1995, the World Bank came out and said, hey, nuclear power, it's too costly and too risky. We can't use it anymore. In 2006, in the United States, we actually had several reactors that were leaking and creating problems in groundwater, and so they were shut down. And so the net amount of nuclear power plants have dropped dramatically since the 1970s. So what are some advantages? There's a large fuel supply available. We have plenty of uranium around. There's not a huge environmental impact with the exception of maybe potential accidents. It releases very small amounts of CO2. It doesn't mess with the ground a lot, land use wise and land disruption wise. And then the accidents have been pretty low cost with the exception of Chernobyl, which we talked about in class. What are some disadvantages? You can't completely run it on government subsidies, which a lot of it is. There's not a lot of high energy yields out of it. There's a huge environmental cost for any major disasters that happen. There's a huge environmental cost not put onto the marketplace. The accidents, when they happen, can be catastrophic in nature. They are areas that terrorists can easily attack and exploit. The more we use it, the more knowledge of nuclear weapons is out there for other people to take advantage of. And then we have long-term storage issues of the radioactive material. So all of these things kind of have conspired against nuclear fuel. So how do we deal with it after it's been used up? So when nuclear reactors in their life, they usually have extremely high levels of radioactive waste. We're talking stuff that needs to be stored from anywhere from 10,000 to 250,000 years. The two ways that it's usually taken care of, the first one is deep burial. This is the main one because it's both safe and fairly cheap. The other one is to change those nasty isotopes into less harmful ones, but that's a little more pricey. So we don't do that one as much just because of the cost. Just generally speaking, there's about 230 nuclear reactors that have and or are going to be put into retirement, and 20 of those have happened in the United States. Most of the reactors, again, only have a 40-year shelf life, and some people are asking to extend that because they're working well. But overall, the net number of reactors has went down significantly over the last decade plus. And then what do we do with those after we use up all those nuclear reactors? Do we just let them be? Do we walk away? Are we required to clean them up? There's all kinds of issues that work with that particular stuff. And so the next idea, though, is nuclear fusion. This is where we're taking small elements. There's two forms of hydrogen used, deuterium and tritium. Those are isotopes of hydrogen. You smash them together and you produce helium, also known as an alpha particle, and you release a neutron. There's not a lot of nasty waste involved in this one. You're basically producing helium gas. Lots of energy yield out of it. So yeah, the ideas behind nuclear fusion are pretty cool. The problem with nuclear fusion is the research. We're in the research stage, and it's been going on for 50 plus years. And the reality is we can make nuclear fusion happen in small scale, but we can't do it without putting more energy into the system than we're getting out of the system. So far, the energy has not been economical, and so we haven't got there yet, but we're working on it. We spent a lot of money in the research, over $34 billion trying to figure it out. If we do, though, we'll have a lot of energy available at a cheap rate with very low environmental cost, which is, I guess, the end goal in general, right? So there's maybe a lot less breakdown of toxic materials. There's no risk of meltdowns and radioactive releases, so it is a good alternative if we can make it happen. All right, that's the end. Bye.